Okay, so today we'll talk about how to bound non-convex optimization problem with with a convex optimization problem, so that the minimization we're going to get for the convex problem will upper bound the minimization of the real problem. And with convex optimization problem, we know how to solve them because every local minima is also a global minima. Okay? So in the context of learning, say, I'll explain it by an example. So say I have a loss function for a model W, which is a set of weights that tries to classify just two categories, 1 and -1, cats and not cats. Okay, so if the real classification agrees with the scalar multiplier of the weights and x, this is positive and this is positive, or this is negative and this is negative. So they agree. If they agree, if it's bigger than 0, okay, then we don't have a loss. Otherwise, we don't agree. Our prediction is not correct, and then we have a loss of 1. Okay, great. So that's a loss function. This loss function is not convex. Okay, it's just a step function, so it's not convex. So we try to bound it with the following function. This is just the maximum of 0 and 1 minus this scalar multiplication. Okay? Now, we need to see two things, that this is a convex function and that it bounds the original loss function that is not convex. Okay? That's the two things we need to prove. Right? Okay. So the fact that this is convex is easy. We already discussed it many times. We just take a maximum of 2.
What does W stand for?
W is just a weight. This is like a vector in Rn, and it's weights. So, and this is like the training data, right? So basically, our model is the scalar multiplier of m and x. That's our model. That's how our model predicts. Or this is our model, or whatever you want to call it. Okay? So a maximum of 2 convex functions is convex, and this is a convex function because it's a constant. So a constant function is a convex function. Okay? And this is a linear function, so it's convex. Okay? So this is convex. It's clear that it's convex.
The maximum of 2 convex function is a convex function?
Yeah.
Doesn't it require proof?
Yeah, but we already did that.
Okay.
Think about it a bit. You can take it as an exercise, but we can talk about it. Generally there's like a set of operations that you need to be aware of that maintains convexity, or if the elements is convex, what you get is convex. And this is very important to understand because it really helps in practice. Like if you have hyperplanes and you take the intersection, it's convex. The intersection of convex set is convex. If you take 2 convex sets and you multiply them by some positive numbers and you take the sum, it stays convex, and so on. There's all these, and this is part of the games we can play with convex optimization, and it's very helpful when you try to solve a learning problem. Okay? So for instance, if you take a loss function and then you go to the average is an integral. If the loss function is convex, the average will stay convex, and so on. So that's part of the game, to understand how what operation keeps you in the convex realm. Okay, so convex. Okay, so it's easy that it's convex. An exercise. Okay, and then the other thing we need to prove is that the loss function is bigger at every point than the original loss function. Okay, so we just take the different cases and make sure it works. So, for instance, I'll give an example. Okay, so say class is 1, and the model predicts that it's 1. So the model is positive. Okay. Then on the one hand, the loss is 0, right? The 0, 1 loss is 0 because there's an agreement between the prediction and the. On the other hand, the surrogate loss, we call it surrogate. The surrogate loss is bigger or equal to 0. Why? Because this is positive. So 1 minus something positive is either positive or negative. Okay? But we take maximum at 0, so it remains 0. So it's bigger or equal to 0. So it's bigger than this. So we have that. Okay, and so on for the other cases. So basically you get that we took a non-convex loss function, transfer it into a convex loss function, and made sure that it bounds it from above. And that will translate into a convex learning problem that will give us a solution that is that bounds from above the solution of the non-convex learning problem.